Hi, welcome back. Last time we talked about creating an update function for our SIR model and seeing how that was all going to allow us to determine a final state given an initial state. Now, one thing that we've really appreciated about our bike share model and our population model is being able to visualize how things are changing over time. And so what we're going to do is we're going to incorporate some data collection into our model so that we can see how these populations are changing over time. So making a better run simulation function. So the question that we care about is, how do we keep track of S, I, and R as they change over time? All right, so answer 1 is going to be that we know that we can use a time series object to keep track of one population over time. All right, the thing is we have more than one population. We have 3 populations here. So we'll need 3 time series objects to keep track of 3 populations. All right, and what we're going to see is that next time we're going to realize that it probably makes sense, instead of you using 3 different objects to keep track of the population over time, it's going to make sense to use one object, which is an array. So next time we'll talk about using one time frame object. But we're feeling already comfortable with time series objects. Let's think about how we create our simulation to use time series objects. All right, so our time series object, remember we put those into our run simulation. So let's create a run simulation function. And as always, we need to bring into our run simulation, we need our system object, with all our system parameters. We need our update function. So before we did this, we brought in our growth function, and this time we're bringing in our update function. We need both of these two things to come into our big run simulation function. All right, so inside this run simulation, we are going to bring in S is equal to a time series, I is equal to a time series, and R is equal to a time series. Right? And so these are empty containers to collect SIR data. All right, so now we have our empty data, empty containers. We need to initialize the first values. So where is the initial data? The initial data is located in init in the system object. So let's access that. So let's define state to be equal to system.init. So now state is a state object. It has an S, an I, and R in it. So let's now define. So this is our S. S is equal to, so no, our initial value was at time 0. S0 is equal to state.s. I0 is equal to state.i. R of 0 is equal to state.r. All right, and so this is initializing the first values of S, I, and R of our time series. I'm going to put a little note here on the side, which is that if our initial time is not 0, then you'll want to replace this by something that looks like S of system dot t0 is equal to state.s. So you'll need to adapt this in case your time doesn't start at time 0. For instance, if you're working with real-world data and your time starts in 1990 or 2000. All right, so now we've started collecting this information. We have our initial time piece, and now we do for t in lin range that starts off at 0, goes up to system.tEnd. So for every time starting now, starting at the initial at 0, going up until the end time, what do we want to do? Well, we want to run our update function. State is equal to update function of state. Oh, I think time came first. Time, state, system. So that's that. Oops, no colons there. Sorry. So we have to run. We have to figure out what the next time t+1 the value is, and then we have to put that information into our time series. So s of t+1 is equal to state.s. I of t+1 is equal to state.i, and r of t+1 is equal to state.r. And then once we do all that information, we need to send this information out. So we return S, I, and R, and you see here that the output is now 3 different time series. So when we run this run simulation, we're going to have to catch all 3 time series. So what's come out of here is, so the output is 3 time series objects, which we can then plot using, so we'll have to catch these objects and then we can plot them. So catch these objects and then plot. All right, so let's head over to Python and get this done. All right, so we're creating this new run simulation. S is equal to a time series, I is equal to a time series, R is equal to a time series, state is equal to system.init. Here we've caught all 3 numbers at the same time. So we've taken state and we've caught in the initial time series S0, that's what state S is. I0 is catching state I, R0 is catching state R. We run this code and this again catches all 3 informations at the same time. So we run this And when we do this, we get SIR. Remember, we have to catch all of this information. And then we can plot them all together at the same time. S-plot, I-plot, R-plot. And when you plot these results, you get this really awesome picture that shows how things are changing over time. So, for instance, we could do them each individually. We could say, let's do I dot plot. And when we do that, we can see that the number of infected people started off at about 1%, maxed out here at about 4.3%, and then went down to 0. Whereas if we wanted to look at what susceptible, that's going to start off high and go down to about 50%, whereas recovered starts off at 0% and goes up to 48%. And this is everything together. All right, so when we come back, what we'll do is we'll start talking about how do we make this work better in terms of a better data structure, and then we can use this to solve some questions that we might have about the simulation. All right, so that's it for now. See you next time.